Okay, hello again. What we're going to have a look at today is voltage and power. And this follows on from our power losses in cables video. And you remember we had our two triangles, V equals IR, and power is I times V. So we know that V equals I times R, and we know that power equals I times V. And we said that from that we can get power equals I, and if I substitute this V for what's on this side here, I get I times R, and that becomes I squared R. Okay. Now, if I do the other substitution here, I can find another formula for power. And what we've just done here is substituted V on this side and put IR in there. But now if I look at substituting the I bit here, well, we know from V equals IR that V over R equals I. And if I substitute this I here for V over R, I get power equals V over R times V, and that becomes V squared over R. And this is very useful for determining the power losses in the load. Now, a power loss in a load really means that you are applying too much voltage to that load and you are dissipating too much power. And we can see that by just looking at a basic circuit. Say that was a 10 ohm load and this is 230 volts. The power dissipated in that load from using this our new formula here, V squared over R, substitute the figures. V squared over R, power equals V squared over R equals 230 squared divided by 10 equals 52900 divided by 10 equals 5290 watts, 5.2 kilowatts. Now, if I just increase that voltage by 1 volt, say to 231 volts, our new power is the same, but this time it's 231 squared divided by 10, and that becomes 53361 divided by 10, which is 5,336 watts. So you can see by just increasing the voltage by 1 volt here, we're driving more current into that load and dissipating more power. So it's very important that you maintain your voltages to your loads because you don't want to dissipate too much power in those loads. Now, this theory applies not only to purely resistive loads, it's most effective in purely resistive loads, but it also applies to inductive loads, because in an inductive load you still have the ohmic resistance of the material, and power is still dissipated in that part of the impedance. Okay, so if I go up to say 240 volts now, P equals V squared over R. If I say 240 volts now, divided by squared divided by 10. That becomes 5784 watts. And you can see from my original 230 volts voltage of 5290 watts, so there's 5290 watts. That's at 230 volts. Gives off that. I've now gone up to 5784. And if you work that out, that comes to an increase of about 9.34%. So there's quite a lot of difference there. So by keeping the voltage down at 230 volts, if your appliance, a purely resistive appliance, was 230 volts, you would save 9.34% if you can keep the voltage at that level. So with 10 volt raise, it's just over 9%. And as a rough guide, for each volt that you increase your supply, you'll increase your power losses by about just under 1%. That's a rough guide. Okay, so that's why it's very important to keep your voltages at the recommended level for your particular appliance. And here we can see a graph. I've just done a rough graph here. 230 volts up to 200. I've done it up to 248 because I couldn't quite get 250 on there. But you can see there that the power increases as the voltage increases. And it goes from 230 volts, about 5.3 kilowatts, and it goes up to about 6.15 kilowatts. It's probably nearer 6.2 kilowatts actually. There's 6.2 kilowatts just off the graph there at 240 volts. Now if your voltage is creeping up to 250 volts overnight, which it often does in some places, then if you've got 24-hour loads on, you're wasting a lot of energy during that night time when the voltage is too high, and you probably need to consider using some kind of regulation. Okay, thanks very much, bye.